In the sort of fundamental theory of computation, essentially when you destroy information, it costs energy. And so obviously the lowest cost of energy in computation if you have a reversible computation. Mm-hmm. In the Copenhagen theory, you're destroying information. But in Everettian, you're not, even though it goes off in different directions. Right. So would there be a measurable energy difference when you examine a qubit, when you observe a qubit?
Yes. So,
all right.
But this turns out the reason why you deserve more words than that, because it's a subtle question, actually. The transition, remember the picture from the wave function being all spread out to looking like that. That seems to be, a sudden dramatic change that could very well involve a difference in energy. The way it works is the localized wave function actually has more energy than the one that is spread out. The spread out one is sort of the resting place for the electron, so the energy went up in that procedure. Now, Copenhagen, people say, how do you test the Copenhagen interpretation versus many worlds? The answer is you can't, not because of many worlds' fault. It's because Copenhagen is not well defined enough. But something like the spontaneous collapse theories really do say the wave function collapses like that, and that should add energy to the system, and over time the universe heats up a little bit. And that is the basis for ongoing experimental probes of those theories. In Everettian quantum mechanics, there's something different you can do, which is literally a paper that a student and I are writing right now. I told you that energy is conserved overall in the wave function of the universe. I did not tell you that the energy of every branch was the same. And in fact, you can set up circumstances where the total energy is distributed unequally between the different branches. So when you measure your qubit, if your qubit is, let's say, in a magnetic field, so that it has more energy if it's spinning one way than the other way, and you measure it, you will have a different energy of the universe if you get one answer than the other, but less energy in the other branch of the wave function.
There's a program on TV last week called Einstein's Quantum Riddle, in which you featured, albeit very briefly, right at the beginning and right at the end. But the scientist right at the end was trying to tell us that quantum entanglement was part of a holographic universe. And all the information that's being sent down to us is what we interpret as space-time.
Right.
Now, if that's true, is quantum entanglement just a byproduct of the Big Bang, or does it exist like some Narnia, a true reality, and all we've got to do is step through the back of the wardrobe?
Yeah. Well, that's a hard question to answer. The good news is I've written a book, and I talk about this in the book. The honest answer, the short answer, just like I gave the previous questioner, the short answer here is we don't know. Okay, so holography is an idea that I did not talk about here, but could be talked about. It's something that seems to become important when the gravitational force becomes strong. So when you have something like the Big Bang or a black hole where gravity is incredibly strong, in a black hole, it seems that what's happening can be thought of as happening at the boundary, at the two-dimensional horizon of the black hole, rather than being distributed everywhere in the three-dimensional volume inside the horizon. That's holography. But it's not true that you're not supposed to think that there really is a two-dimensional space in the wardrobe where you could go visit. It's just that there are different ways you can talk about the world we live in. One way, it looks three-dimensional. Another way, at least under some circumstances, it looks two-dimensional. The real lesson is the dimensionality of space is overrated. It is not something that is fundamental. It is something that emerges under different circumstances in different ways.
This guy was saying that quantum entanglement actually exists at the edge of the universe. Surely it's all around us.
Yeah, he wasn't actually saying that. He gave you the impression for saying that because there is a toy model of the universe called anti-de Sitter space, which is certainly not our universe, but is very mathematically pretty. And therefore, there's a certain subclass of physicists who like to pretend that we live in that universe. because they can solve the equations in a very direct way. And in that universe, you can think of everything that happens in the universe as living on a boundary that is just two-dimensional at the edge. Sadly, that is not our universe, and so applying the lessons from that analysis to the real world is a little bit tricky, which is why I say at the end of the day, we don't know.
Yeah, my question is, in the average interpretation, a measurement splits the universe, and yet we still haven't defined what measurement is.
Yeah, no, I did totally define what measurement is. It's exactly this. Measurement is when the quantum mechanical system becomes entangled with its environment.
But at what point? I mean, how do you know that at that particular point there's a measurement taking place?
There's an equation that you solve, and the equation says exactly how much entanglement there is at every moment in time. The reason why the extraordinarily smart people who invented the Copenhagen interpretation got away with it is because the speed at which decoherence happens is very, very fast. You know, we had a little joke about the 10 to the minus 11 seconds that it would take an electron to spiral to the center. The cat would decohere with its environment in less than 10 to the minus 21 seconds. So effectively, when decoherence does happen, it happens right away.
Mind-blowing. It will keep me busy for a long time. I'll read your book, certainly. Thank you so much.
Thanks.
And it's great to be so near to you. So I've been thinking a little bit about this dark matter and dark energy, and your idea of, correct me if I'm wrong, of gravity sounds like an entanglement effect, and how the gravity is intense or less intense is also a function of entanglement, right? Amazing. I'll think about it. So how would you put this dark, it sounds like, sorry, my French, BS, when you talk about dark matter.
That's English. No, you got it right. Yeah.
Thank you.
Yeah.
So how would you say, how could you explain this dark energy? It feels like entanglement, right?
Yeah, well, so that's another question to which the only strictly correct answer is we don't know yet. We don't know what dark matter and dark energy are. The short version is, in the 1990s, for those of you who spent your time more productively, we discovered the inventory of the universe. You know, the stuff that you and I are made of, tables, chairs, atoms, particles that we've discovered in laboratory experiments, makes up 5% of the universe by energy. Another 25% is some other kind of matter, some other kind of particle that we've not yet seen in an experiment, cleverly called dark matter. And the other 70% is something called dark energy, which isn't even a particle. It's an energy that suffuses all of empty space and pushes things apart. There's no reason to think that dark matter and dark energy are anything other than another kind of matter and energy. It's not different in spirit than electrons or protons or stuff like that. It's just that they're dark. But you know what? The air in the room is dark. Dark in this case means light goes through it. It really means transparent. That's what dark matter and dark energy are. So we know that there are airs in the room because when I move my hand, I feel it. Even though it's dark, I can feel it. And likewise, we know that there's dark matter and dark energy in the universe because it affects gravitationally the motions of galaxies and particles and other things. So I don't think we're going to need to dig into the nuts and bolts of quantum gravity to understand dark matter and dark energy once we finally do.
Interesting question for you, but though in all your multi-universes, does time go in the same direction? Does time ever go backwards in your equations?
In the things that I've talked about today, time always goes in the same direction. So the picture I showed you, there's an arrow of time. Look, it's right there on the left. Points upward, okay? So yeah, time goes in the same way in every universe here. Now, there's a much longer, everyone's asking questions that deserve an hour. So like, how many hours do I have here to answer these questions? There's a difference between time as a thing, as a coordinate on space-time that measures when you are, versus the arrow of time, which gives you the directionality, the past versus the future. You could imagine a universe in which time existed, but there was no arrow of time whatsoever. And you could imagine universes in which the arrow of time was reversed, even though it came out of the universe that we live in. None of that has any direct connection to what we're talking about here. there. So those are perfectly permissible cosmological speculations. Luckily for you, I wrote a book about them called From Eternity to Here, but it doesn't tie in directly to this. No, time moves the same way in all of these multiverses, yeah.
Hi, yeah, I was just wondering if you had, or if you could explain the dual slit experiment in terms of the many worlds theory, or if that has a kind of simple explanation.
Yeah, sure. So again, you've been cheating on me. You've been learning quantum mechanics in places other than this lecture. So there's something called the double slit experiment, where you pass a single electron through two slits. You couldn't do that if it were a particle, but if it's a wave, it can go a little bit through both slits, and then as it goes through, the wave sort of spreads out in ripples and can constructively interfere or destructively interfere, which means that you're likely to see the electron some places and not others. So if you do this over and over again, you see an interference pattern that tells you that indeed the electron was a wave when it went through the slits. But according to the rules of quantum mechanics, if you just look at the slits while the electron is going through them, you measure which one it went through, and then it's like a particle. It's not like a wave anymore. And indeed, miraculously, when you do that, the interference pattern disappears. You have stopped the electron from going through both slits. So many worlds has no problem with something like that. All you say is that when you measured the electron going through the slits, that electron became entangled with you or whatever the detector was. The wave function of the universe branched, and rather than there being one universe in which the electron's wave function could interfere, there are now two universes, and the electron's wave function can no longer interfere, so the interference pattern goes away.
Due to the acceptance of the Big Bang, does that mean every particle in the universe is entangled, or future particle will be entangled? And are tachyons the same as entangled particles, or are they something separate?
Good. So tachyons don't exist. That was easy. Tachyons, if they did exist, would be particles that travel faster than light, and that would be a disaster for all sorts of reasons. The other question about the entanglement of all the particles is a harder, trickier question, and in fact is closely related to this arrow of time question. Entanglement leads to entropy. When two particles are entangled with each other, you know less about the state of either one of them, which we can mathematically quantify by saying it has a higher entropy. The early universe seems to have a very, very low entropy. Near the Big Bang, the entropy of the universe was very low. So what that really means is that particles were not entangled near the Big Bang, and that then they become gradually entangled, and that's why you start with one big branch, and it goes more and more as particles become more and more entangled. What we don't know is where that asymmetry comes from, why there's a difference between the top and bottom of this picture, why everything was unentangled at the start and becomes entangled later. We don't know. I'm older than 48, so I'm too late to come up with great ideas to explain these things, but I encourage the youngsters in the audience to put their noggins to work on these questions.
I'm trying to put my head around how many multiple universes there are. And it's gotten to the point that it's almost inconceivable. For example, the cat. We could have a sleeping cat. We could have an awake cat. We could have a sleeping cat with fleas. We could have an awake cat that's having a fur ball. We could have an observer with fleas and an observer who's having a coughing fit. That whole we can have you standing over there as opposed to standing over there, and me holding this in my left hand. Now, each one of those splits like that for every single breath that all of us are taking. I've kind of got lost there. How does that, I mean, that's really nice because there are like 12 of those.
Yeah.
But
it's actually much worse than that. One of my favorite facts from your book is that the human body has about 5,000 atoms that undergo radioactive decay every second. So that's 2 to the 5,000 branches every second. And that's just me.
Just because you,
how many have I had just
I know.
now?
Right.
So yeah, it's a lot of branches.
What are you doing?
So how does that work with a multi-universe in a way that humans can comprehend that?
Well, imagine the real numbers between 0 and 1. Divide them in half so that you have the numbers between 0 and a half and the numbers between a half and 1. and then divide them in half again, between numbers between 0 and 1/4, and 1/4 and 1/2, and 1/2 and 3/4. You never run out of numbers.
How thin do the universes get?
So
do they disappear? They're so thin.
this becomes embarrassing at some point, but the answer is we don't know.
Thank you.
The slightly longer answer is, I wrote a book,
Yeah, I'm there.
and I talk about this. We don't even know whether the total possible number of universes is finite or infinite. And in my mind, this reflects the fact that we haven't been trying to answer this question. We haven't really been focusing our brains on the foundations of quantum mechanics to the extent that we should have in the last 90 years. I can give you a good argument that the number is infinite, in which case there's plenty of room. I can also give you a good argument that the number is finite. But if the number is finite, the kind of numbers that it might be are things like 10 to the power of 10 to the power of 123, which is plenty of room for all the divisions that you need. Yes.
Then the universe gets very thin and it becomes something other than another universe. It becomes another wave?
No, once you're in the universe, so there's a couple things going on here that I should also mention. For one thing, breathing does not branch the wave function of the universe, okay? The wave function of the universe doesn't just branch because you do something or don't do something. The wave function of the universe, as we said before, branches when a quantum mechanical system in a superposition becomes entangled with the environment. That happens a lot, but it doesn't happen just because something happened, right? The many worlds interpretation of quantum mechanics does not say there's a world in which every different possible thing happens. It says the wave function obeys the Schrödinger equation. And the Schrödinger equation is going to lead to some kinds of universes and not to others. So there's a lot of universes, but there's not literally a different universe, a different branch of the universe for every possible thing you can imagine. But nevertheless, there is something going on in your question. The thinness of the branch you're in is not something that you have any idea what it is. Like right now, we're in a branch of the wave function. How thick is it or how thin is it? Yeah, you have no idea. There's no measurement you can do. There's nothing you can do. You don't feel thinner, sadly. It doesn't, like you can branch the wave function. It doesn't have any effect on how you feel, okay? But there is a process going on. There are two processes going on that are not completely distinct. One is all of these branches are separating from each other, differentiating from each other. The other is, in each universe, space is expanding, stars are using up their fuel, galaxies are moving away from each other, the universe is emptying out. So even though all these branches are becoming different from each other, within each branch, the universe is kind of moving toward an identical future. So when you get far enough in the future, even though there's a lot of branches, they all look the same. So at that point, way, way, way in the future, literally a Google years from now, it will be difficult to even talk about different branches of the wave function. That will no longer be an appropriate description.
In a kind of cartoon history of quantum mechanics, Einstein's portrayed like the kind of Luke Skywalker or Han Solo, hero of the resistance. And Bohr is Emperor Palpatine. He's the dark force trying to hold back a realist interpretation of quantum mechanics. Now, sadly, Einstein died in 1955, and Hugh Everett's thesis wasn't available until 1957.
Yeah.
But have you thought what Einstein would have made of Everett's proposal?
Have I thought of it, you say? Have I thought about that? The epilogue of my book talks about exactly this. And of course, the only fair answer is we don't know what Einstein would have thought about this. But it's more than just, it's a hypothetical question, but there are two very strong commitments that Einstein had, which many worlds goes in one direction for one and the opposite direction for the other. One is he was very, very committed to space-time. He liked space-time. He liked there to be locations of things. I mean, he had a right to be fond of space-time, being Einstein, right? So he liked the idea that space-time was a thing, whereas I just told you a story where space-time is kind of a fuzzy approximation that is no longer fundamental. He would not have liked that, okay? He would not have liked the fact that there are not definite outcomes in any one universe. On the other hand, I think he had an even stronger commitment to things making sense, to there being answers to questions, to there being equations and patterns and laws of nature that gave unambiguous answers to whatever kind of question you ask. He wanted a mechanistic description of what happened in the world. The title of this book, Something Deeply Hidden, is a quote from Einstein. It's a quote that he gave when he was reminiscing in his later years about growing up, and he was given a little magnetic compass, right? A famous story that he tells. When he was a kid, he was given this compass, and he's like, I can move, and no matter where I move, it knows where north is. How does it know? And he says there must be something deeply hidden that explains that. And that was his objection to the Copenhagen interpretation of quantum mechanics, that it just seemed like a mystery. And many worlds, like the other alternatives to it, attempt to provide that deeply hidden thing. He would have liked that.
He was also rather anti-metaphysics and dismissed Bohm's interpretation as too cheap. So I do really wonder whether that's a correct characterization of what Einstein might have made of it.
A lot of the way that we use quantum mechanics is largely statistical and to do with probabilities. And so if I understand it right, the many worlds kind of says that every possibility or everything can happen. So then are the worlds where, for example, the experiments that determined Bell's inequality theorem came out the other way, and everybody's understanding of quantum mechanics is totally different, and there's a Sean Carroll kind of standing there looking and saying, well, actually, quantum mechanics is something completely different to what you're saying it is today.
Yeah, so there's a couple things going on here. One is, I can't emphasize strongly enough, it's not that everything happens, okay? For example, a very, very simple example is there's no universe in which a proton turns into an electron. That would violate the conservation of electric charge, and that literally never happens according to the Schrödinger equation. So there's plenty of things we can imagine happening that just don't. Still, as we discussed, there's a lot of things that happen, and one of them would be I can line up a whole bunch of particles that are equal superpositions of spin up and spin down. I can measure all of them, and I can get spin up every time, which would be really, really unlikely, but many worlds says it does happen in one branch of the wave function. I did this experiment for the book. I ran a quantum random number generator. I generated 50 quantum bits, either zeros or ones. And I got 26 zeros and 24 ones. So roughly 50-50. That's good. And then I put the number in the book, which means that there are 2 to the 50th different versions of the book out there, textual variations out there in the multiverse. But in one of them, it was a 0 every time. And you say, well, what did that version of me think when he got zeros every time? And of course, what he thought was, this isn't a quantum random number generator at all. Someone just broke the machine, right? And there's nothing you can do about that. There will be, as your question implies, there will always be, in this version of quantum mechanics, versions of the world in which things that are overall really, really unlikely come true. And the people in them, they're out of luck. Sucks to be them. But they're very, very unlikely. So that you really gotta, if you buy this story at all, you really have to take seriously the idea that not all the worlds are created equal.
I'm not sure if I understand correctly here, but we talk about sort of the weight or the thickness of each of the branches, right? So if I understand this correctly, that the thickness or the weight is sort of synonymous to the energy. And if that's true, then every time a quantum interaction happens in our universe and it splits, then the 2 branches in my mind would seem to contain the same amount of energy because there's no change in the amount of mass that they contain. So does this mean that the energy is taken from another branch somewhere that then contains emptiness? And what happens when the energy from there disappears? Do we know anything about this?
Yeah, so this is entirely my fault at doing a bad job of explaining this, but to my credit, I did say I would do a bad job of explaining it. The amount of energy that contributes to the whole wave function of the universe is the energy in each branch times the thickness of the branch. So when one big thick branch divides in 2, the amount of energy in each of those branches is basically the same as the branch it came from, but the thickness is only half as big. So the total contribution has remained the same.
You explained that it was possible to design an experiment where the energy was divided unequally between the two branches. Can we do that with entropy and information? Can we dump our unwanted entropy into another branch and get rid of it?
That's an excellent question, and because unlike all the other questions, I know what the answer is. And the answer is no. In fact, let's be super clear about this energy thing. Energy can be distributed unequally between the branches, but you can't control which branch you end up in. So if you do an experiment where the energy could be a little bit higher or a little bit lower than where you started, maybe it will go up, maybe it will go down. There's no perpetual motion machine possibility here. And even with that caveat in mind, entropy is a trickier customer, and it just goes up. Sorry, it just goes up no matter what we do. We can sort of play with it in open systems that are connected to the rest of the universe, but as far as the universe as a whole is concerned, I should be more careful than that. It goes up almost all the time, but exactly as you can get a weird branch of the wave function where all the spins give you spin up, you could get an unlikely fluctuation into a lower entropy state. That is possible, but it's not controllable or predictable.
Well, I think we should end on a
like
question
so
you need
many
to
things
answer
in life, not controllable or
and
predictable.
now we can all go get entangled outside. Thank you
like
so
that.
much, Sean Carroll, an absolutely mind-blowing
Thank you very
talk.
much.